what should we look for towards ensuring that more public research is credible? Should we look for significance, for innovation, or for rigorous, quote-unquote, reproducible approach to research? What should really be our dream about research, the best of research? Significance is something that most people are talking about. Scientists, editors, funders, all NIH grants, they have to show that what you do is significant. However, I'm afraid that it has really lost its value because everything is significant. Almost all papers claim that they have found statistically or conceptually significant results. Recently, along with David Chevalerias, we looked at the entire Medline from 1981 to 2013. Almost 1.5 billion abstracts with p-values, and 96% of them had statistically significant p-values. So everything is significant. The discriminating ability of significance, either statistical or conceptual, is very, very weak. How about innovation? There's hardly any reliable method to predict innovation ahead of time. The vast majority of honest and excellent scientists working very, very hard will never discover something that will be a Nobel Prize. And even if they discover a Nobel Prize, it may be lobectomy, who knows? It's very, very difficult. It takes also many years and often decades to materialize and translate itself. So at face value, an editor is in a miserable position to try to judge that this is innovative. It's literally impossible with very, very, very few exceptions. What is the typical recipe of research practices? Usually we're dealing with that pattern of a solo, siloed investigator trying to compete against everybody else. So every scientist competing against those other 15 or 40 million scientists out there. Not very good odds. Small sample size studies. If you're alone, you cannot run very large studies. Cherry picking of one or best hypothesis out of many hypotheses being pursued. Post hoc analysis being the predominant theme for most of what we do. P-value of 0.05 is enough, or even 0.006 or 0.08 would do with a little bit of spin and creativity. No registration, no replication, and no data sharing. So this is the paradigm of the scientist who's out there struggling to survive. Now, empirical studies show that that paradigm, when it works with cherry-picking small studies, one hypothesis at a time, doesn't really work. And this is when we have done replication studies to try to see how many of that cherry-picking one hypothesis at a time type of research gets validated. Now, replication in most fields is me too, don't do that, you're wasting your time, nobody's going to fund it. But for some fields like genetics, suddenly became very easy because the price of running genotyping became 100 million-fold less within a few years. So now we're running the whole genome, and we can also test what happened to those SNPs and variants that we thought we had discovered in the past as being genes related to various diseases or phenotypes. So when we did that, which now is a secondary exercise, the replication rate of candidate genes replicated through the much more rigorous GWAS studies is 1.2%. So for example, for smoking, 10 years ago, we thought that we had found 359 gene loci that regulate smoking behavior. When we ran GWAS, only one of those survived, and now we're up to 10 that have very rigorous support. But the replication rate was extremely low. Who else might be doing some replication efforts? A pleasant surprise. I think that I have been a nuisance for the industry with all the comments that I have made over the years about conflicts of interest, but in some regards, in the last few years, they have become my heroes because they have started doing lots of replication studies. Now, it's not that suddenly they want to save the world. I think the main reason is that they're investing a lot of money to try to translate basic research into applied drugs and other technologies. And these replication studies of preclinical research done by academic centers gives replication rates of 15%, 20%, actually 10 to 25%. So very, very low. So how can we solve some of these problems that are not necessarily related to research methods alone, but the whole system and the way that the system of publication and of research is operating. Some solutions have been identified that have worked in specific fields, and if they have worked and they have good documentation that they work in one field, maybe we need to consider how to transplant them in other fields. Other solutions are more speculative. They're wonderful ideas, but no one has really tested them out yet, or is using them. Scientists and journals and funders may be using them, but with no empirical support. No matter what, I think we need empirical evidence for all of these proposed solutions, because there's always the chance that we may do worse than the current system in whatever we try to fix. So I would say do no harm is a number one issue. Here's a list of such solutions I would like to discuss, and we can go through each one of them. One major progress, I think, is the advent of team science. I showed you the example of genetics. I think if you had continued doing research, each one of us alone, and publishing small studies here and there, nothing would have happened. So now we have the ability to generate reliable knowledge. This is the Manhattan plots from a paper on smoking behavior genetics. And there's hardly any survivors. There's only 4 genes that survived out of a coalition of about 200,000 participants and 100 research teams and about 1,000 investigators being involved in that, as compared to 359 genes that we thought we had found in the past. But at least now we know that this is reliable. We can take it to the next step. We can see what these genes mean and whether there's some implications about acting on them. Next one. One major question is, who's going to do the replication studies? If you have everybody in the world working on the same topic, joining forces, this is an ideal situation. But in most cases, you have some people in the discovery front, and then who's going to do the independent replication? Will it be the same investigators? Maybe there's some sort of bias if you just ask the same people to replicate their own work. Should it be different investigators of the same school? There could still be allegiance bias. Should it be different investigators of competing theories or hypotheses, kind of contrarian replication? You know, you ask your opponents to try to replicate what you're doing. If they can replicate it, then that's very good news. A combination of the above, or should it be open to the wide public, or I should call the wild public? You know, it can be both. Anyone having access to everything, the raw data, the protocols, the materials, and just having the opportunity to take a shot. This is an interesting idea. I'm very sympathetic to that, and I'll discuss some of these options, but there's also some caveats. Registration is another possibility. So how can we make sure that we haven't missed studies that are out there? We can ask investigators to register. So for clinical trials, this has been successful, or at least substantially successful. We have clinicaltrials.gov and other registries where we can note the existence of a randomized trial, so it doesn't really disappear. For other types of research, the problem may not be so much studies that exist and have not been published. To me, the major problem is the studies that have not existed yet but could potentially exist. So if you have a database, and much of research currently is in silico, you have potential studies that may exist at 3 o'clock in the morning when you click on your computer and you generate 1 million chi-square tests. And the question is, how many opportunities for generating these chi-square tests one has? It's like mapping nuclear weapons. You know, John has so many petabytes of data in his computer. He can destroy the world if he starts performing analysis. Or Mike has even more. I think it's important to know what is the power of the available data sets, rather than just launch all these nuclear weapons and really destroy everything. We can think of levels of registration. Level 0 would be no registration. I'm perfectly happy with that. I'm a strong proponent for registration, but I'd rather see that someone is saying, well, this is not a registered study. It's a completely exploratory analysis. It's data dredging at its best. That's wonderful. And lots of very interesting discoveries may come out of data dredging exploratory studies. The question is, and the issue to me, can we acknowledge that? Can it be transparent that this is really what happened? Level 1 is registration of a data set. What I mentioned earlier, you know what is the nuclear arsenal and what is the potential of running analysis. Level 2 is registration of a protocol. You have a very specific set of hypotheses and how you want to go about them. Level 3 is registration of the analysis plan, which is different from the protocol. I mean, you can have registration of a protocol, but the analysis plan may be completely open for flexible solutions, and you can still get lots of very different results depending on how you analyze the data. Level 4, registration of the analysis plan and the raw data so that others could access those. And level 5 would be open live streaming, which means that I open my computer, you can see what I'm doing, you can send me real-time comments that don't do that, it's really stupid. Use a different test, or you need to do that first, or you're doing it wrong. I think that we don't know exactly what level of registration is the best for each type of study. I would argue towards trying to push the agenda more towards higher level of registrations, but also generate some empirical evidence on what level of registration would be optimal for each type of research that we are trying to do. How about data sharing and sharing of protocols in real life? This is an empirical study that we published in PLOS One a few years ago, looking at whether the top 50 impact factor journals across science have policies in place for sharing of data, of protocols, of materials, and also whether it was a prerequisite to publication. You see lots of green color, which is good news. It means that most of these journals were sensitized, so their editorial policies did note that they wanted that to happen. However, the last column, which is very tiny font, has lots of zeros, and this is how many out of 10 papers from each journal that we looked more in depth actually adhered to these policies. So people are sensitized, but it doesn't really happen in real life. We are repeating that exercise currently with colleagues from NIH, and I'm curious to see what is happening about 5 years down the road. Sharing data is a wonderful idea, and I'm very much in favor of that. However, it could have lots of caveats, and it could have a lot of obstacles. About a year ago, along with Peter Doshi and Steve Goodman, we tried to make a list of the debated issues and challenges on the optimal procedures for data sharing for clinical trials, which is one big domain of research. You can imagine that if you move to other types of research like observational epidemiology, or if you depart from biomedicine, things can get even more complicated sometimes, or maybe easier in some regards other times. But really there's a lot of challenges. I think that we need to think very carefully about how we can optimize data sharing. Currently, I estimate that less than 1% of published data are shareable. And it may be even an overestimate. We're trying to put a number into this, and we'll have an answer probably in the next few months with a large random sample from the entire literature. I think clearly we can do better, but how exactly to do it, it's quite an interesting ordeal. And I would argue it's going to be much easier to do it for future studies, for studies that are starting now, for studies that the funders have control of making it a prerequisite to funding to get them started. Rather than for studies that happened 20 years ago. And this can create lots of tension. I mean, it can also lead down the wrong path. For example, you have heard about the suggestion of not allowing the Environmental Protection Agency to use any evidence in claiming that some pollutant is a pollutant unless the data were readily available to public view. And this means that since all of these studies started 20, 30 years ago, none of that is readily available. None of that probably can easily become readily available, with some exceptions. It means that suddenly we find ourselves that I can start enjoying pollutants for breakfast and lunch and dinner because nothing can be shown that it is harmful. If we have raw data, the next question in the current situation, what are we going to do with them? Who's going to do what? So this is a pilot project that I tried to do with Nature Genetics a number of years ago. We approached Nature Genetics that had a policy that in order to publish microarray studies, authors had to deposit raw data, protocols, algorithms, everything in public view. It's a prerequisite to publication. So we gathered 4 teams of microarray analysts, the best in the world. This is the highest impact factor journal in genetics, very high quality research being published there by the best scientists. We tried to see, can we repeat analyses that are published based on seemingly everything being available? This is a prerequisite to publication. And when we tried to do this, apparently we only got 2 out of the 18 papers being repeatable. The reasons that the other 16 were not, data were not available, even though they were supposed to be. The software was homemade and it had disappeared. The methods were unclear, so leading experts and analysts could not understand what exactly had happened. Or everything was clear, but the result was different. So this is a creme de la creme situation. How about in other situations where you really have the Wild West in terms of who's doing what? I'm curious to see what will happen. I think that we will go through some transition phase if we manage to open more quote-unquote sensitive data to a wider public. Another example is reanalysis of randomized clinical trials, where recently we tried to map existing reanalysis from randomized clinical trials where the raw data had been used to reanalyze the same hypothesis on the same outcome. We found very few, fewer than 40 such reanalysis across the literature. I'm sure that we missed some because it's not easy to track reanalysis. They're not really tagged as reanalysis in PubMed. What was interesting is that most of the time these reanalyses had been done by the very same authors or included the same authors as the original paper. So it was not really an independent validation of the original analysis. Even more weird, 35% of the time these papers claimed that the conclusion about who is going to be treated and whether patients should be treated or not was different compared to the original paper. So it was the same authors reaching a different conclusion using the same database on the same hypotheses, but with a new method. And most of these people were very happy about that. It was not that they were apologizing that we did it wrong the first time. It was our new method shows that more patients need to be treated, or different types of patients need to be treated. Why is that? Well, the main reason to me is that the research system is such that in order to publish something, you need to claim that you have something new to say, something novel to say. So if that means destroying your original paper, well, carefully and gently, that's what you're going to do. Another possibility is to try to make conflicted stakeholders and conflicted authors more difficult to invade the publication space. Now, this is not easy because much research has conflicted stakeholders, and almost all authors are conflicted. I mean, I'm conflicted to try to defend my work. I'm wrong. No way. So at least we need some more transparency, and there's a lot of empirical work that shows that much of the time we're missing information on conflicts of interest. And then we need to decide who should be the sponsors and the authors of sensitive studies like randomized trials, for example. I have argued that companies should not sponsor randomized trials. I think that they should just give some money to FDA or NIH or PCORI or whatever, and independent scientists should design the research agenda to run these studies. Who should be the sponsors and authors of meta-analysis? Recently, we realized that in antidepressants, in the last 6 years, there's about 200 meta-analyses. About 80% of them are sponsored and or authored by the industry. And always they have no caveats about antidepressants. While the few that are by other authors, about 50% they have caveats about antidepressants. Who should be the sponsors and authors of cost-effectiveness analysis? This has been recognized for almost 20 years now. Again, depending on the assumptions and what you use for baselines, for modeling, you can get very different results. Who should be the sponsors and authors of guidelines? Continuously, one debate after another. The latest probably big debate was about statins, where people thought, well, can you have these people who may have conflicts of interest participate? It's very, very sensitive issues. Next, better statistics and methods. That probably can take us quite a long way. There's no end to better and more transparent and possibly registered, depending on the type of study, statistical analysis plans, statistical training and improved literacy and numeracy of the scientific workforce. I think that statistics are moving forwards and people are more sensitized to that need, but there's still big islands of science where there's very little quantitative aspect to the way that the research is being conducted. Reporting standards. Several authors previously mentioned the importance of reporting standards, and I think that PLOS medicine has been a leader in that field. I think that they have been very useful in improving the transparency of different types of research and communicating what exactly has been done. Equator has amassed a large number of such standards. Not all of them are necessarily perfect. I think that there's plenty of room for improvement, and there's also plenty of room for how we implement them and how exactly we test what their impact has been in the literature and the credibility of the literature at the end of the day. Then there's many other initiatives that are trying to probe into the reproducibility of different types of studies and designs. I'm just going to mention a few of them. The Center for Open Science that Brian Nosek has launched is focusing on psychological science. The Reproducibility Initiative is currently trying to reproduce the most high-impact research in cell biology, but also other fields. Metrics, our new center at Stanford with Steve Goodman, we're trying to create a connector node or a hub for scientists working on research and research policy and research practices and how one could optimize those. And to achieve some real progress, the last few slides that I want to show you are dealing with probably what is the most essential. We need to have the reward system in place that would reward the right type of research, reproducible practices, and reproducible research. For example, one idea about re-engineering the reward system is to introduce some other aspects between just publications and grants. So this is what I call the PQRST index. P stands for productivity, so it's indeed papers published, but I would say focus on maybe the high impact papers, the most essential ones, rather than just ask people to publish like crazy. Q, quality, and I discussed a little bit about how some key quality features could be decided within the community and then appraised for scientific work. R, reproducibility, get credit for reproducible research if something gets replicated. S, getting credit for sharing of data or other resources. And T, translational impact, getting credit if what you do eventually works, translates to something that is applicable and meaningful and does have efficacy at the end of the day. In order to do that, we may need to change the currency exchange rates that we're utilizing. So this is a proposal of two possibilities of changing the currency exchange rates that I discuss in the upcoming PLOS medicine paper. In the current situation, which is the first column, all publications count. Of course, people are looking at the impact factor and the journal where it's published and da-da-da, but you know, people say, I have one paper in PLOS medicine. They don't care whether it's replicated, whether it is translated, or whether it is refuted. Then sharing of data and other resources doesn't give you any credit. If you contribute to peer review, as Hilda said, currently the reward system is not there. You get no credit. Contribution to education and training, improving the background tools of scientists, again, very little value. Grants count a lot. So here I estimate that one R01 can be traded with 5 good publications. You know, it's like trading cards. And then there are other wealth items. So an assistant professor is 3 research dollars or research money equivalent. An associate professor is 10 points. A tenure professor is 20 points. If you're a leader of a team, for each doctoral student that you get, you win 2 points, which means that you can trade 1 postdoc for 2 papers, or 2.5 postdocs for 1 R01. You know, that's the latest stock market exchange. And then administrative power, networking, lobbying. So if you become dean, or people know that you're the leader of a professional society, or then can be up to 200 points. You know, so you may have no CV to talk about, but you know, if you have that power, then everybody's kneeling before you. And then there's 2 possibilities of changes. Change one possible disruption. Publication per se has no value, but if it's a replicable publication, you get 2 points. If it gets translated also, you get 5 points. If you get refuted, you lose 1 point. In that same change, if you just have power, this doesn't really count. Grants continue to count, but also educational contributions, peer review contributions, and data sharing contributions, they also have value. Change number 2, even more disruptive, you have emphasis on replication, on sharing, on contributions to peer review, education. If you get grants, you lose points, you know, because you got money, you're wasting money. You'd better do something to counterbalance that. And also, along the same lines, if you get more postdoc students to work with you, you lose money, you lose points, because you're wasting people's time and effort. Again, you'd better put it to some good use. And if you have power, you can lose up to 200 points, because you have power. Again, you'd better make some good use of that. And that system is also kind of an anarchic anarchy prototype, where you have no titles, ranks are demolished. So is that better? I'm not saying that it is better. It's a speculative system. Obviously, if people lose points for getting grants and getting leadership positions, you will not wish to get a grant. Nobody will apply for you know, big grants in particular. No, I don't want that, please. You know, if you are asked to take leadership positions, again, you will run away because you're losing points. But so we have to find some balance between these themes and really be explicit about what is the exchange market like. What is the stock exchange for reward in research and academia? Finally, I want to add with 2 caveat slides. I have argued for 20 years now that we need more replication and more reproducible research. Well, we can reach the other extreme. We can reach the situation where we just have too much replication. This is one example of a meta-analysis that has been done 11 times when we published that paper. I think it has been done 14 times by now on the very same question, practically using the same trials and reanalyzing them again and again and again, and always reaching the conclusion about a very similar effect size. I think this is a waste of effort. We could have done maybe 2 or 3 just to make sure we get the same results, but why have 11 or 14 meta-analyses on the same topic? And then the other caveat is that we have to take into account that our world is changing very rapidly. So this is one example. Within a few years, there's going to be far more English language papers published from China than from the US. This is already happening in some fields. So this is what's happening for English language papers indexed in PubMed in the field of genetic meta-analysis. And the tall bar, the blue bar, is not the US. The blue bar is China. China was practically nowhere 6 years ago, and now it covers about 75% of the production of genetic meta-analysis in English language journals, in very good impact factor journals. These meta-analyses, they look very nice if you look closely. So their organization and methods and reporting standards, on average, they're wonderful. However, most of them are just wrong. And the reason for that is that they have to use the fragments of published data, mostly from the Candida gene era. They do not have access to the very large databases of the big consortia of the genome-wide agnostic era. So they just use 5% or 10% of the data. They conclude that a Candida gene is significant, but that very same gene has been tested in very large studies, and we know that it is not. So how do we avoid reincarnation of some of the mistakes that we have made in larger scale in the future? This is quite of an open challenge.